move. So this ties in velocity, but it really doesn't matter. What we should know, Marcus, is that if I integrate this function that's in here, because its units are meters per minute, I will get meters. If I derive this function, I will get meters per minute squared, which is called acceleration in this particular case because it's meters per minute squared. Okay, so we got Johanna, I don't know, what do you guys think? Johanna. She's running on a straight path, okay? Her velocity is given here, and they're going to ask some questions about it. What does they tell us about this? Great. Use the data to estimate v prime. If you have to find the derivative from a table, you just find the slope on that interval, okay? 16 would be on this interval, so we're going to find the slope. Now, when you write this out, you should write what you're approximating. V prime of 16 is approximately equal to. You should also write just the formula we're using here. We're doing v of 20 minus v of 12 over 20 minus 12. And that's equal to, it's not approximately equal to, this will be equal to what we do. That is 40 over 8, which is 5. Now remember, the units on that 40 are meters per minute, and the units on that 8 are minutes. So this is 5 meters per minute squared. Okay, that's like a 1-point question, maybe a 2-point question, depending on the rest of the parts. Okay? Okay. B says, explain the integral of the absolute value of velocity, which we talked about last class, I believe, and approximate it using a Riemann sum with 4 subintervals. So let's again talk about what the integral of the absolute value finds. Before we get into that, who remembers what the integral of velocity finds? There's a word for this. Displacement. It's the change in the position. That's just a fancy word because the integral of a rate of change is always the total change in the amount. Okay? So if velocity is our rate of change, then the amount is like our position. So this is change in position. It finds the position at the end minus the position at the beginning. It's called displacement. Okay? That's the integral of velocity. It will always be displacement. No, this is not an absolute value. The question asks about absolute value, okay? This one's not. This is just displacement. If you integrate the absolute value of velocity, all that does to the velocity is it takes all the negative parts and makes them positive. So it's like you're always moving forward now, kind of. Okay? This is not displacement. What's this one? Distance traveled. It is not simply x of b minus x of a. It is most definitely not, I'm going to write this, and I even shouldn't write it. I'll write a big not equal to sign. It is not equal to, kids, the absolute value of x of b minus x of a. It doesn't work like that. You can't just treat absolute value like it's not there and then put it back in at the end. Okay? It does not do that. So when they ask you to integrate an absolute value, it'll be one of 3 things. You'll have a calculator, which means you can just put absolute value on the thing and integrate it with a calculator. That's easy. It'll be a table to integrate absolute value there, just make all the values positive. That's what absolute value does. Okay? Or it'll be like an actual function where you have to find the area. So I think I did an example like this last time. But let's say this was our velocity curve. If the area in here is 4, if the area in here is 8, and the area in here is 3. Does it make sense? Now, again, this is velocity. It's telling us that we move forward 4, backwards 8, forwards 3. Make sense? I don't know where I started, so I don't know my position at any time right now, but I know how I moved. So if I had to graph that motion, if I started somewhere, I'm going forward to a distance of 4, then I'm going backwards 8, which puts me at the position of -4, really, from where I started, and then I'm going forward again 3. What would my displacement be on that interval? -1. I'm 1 unit, meter, feet, whatever it is, behind where I started. Does that make sense? But if I integrate the absolute value of velocity, then this curve doesn't have a negative area. It's got all positive area. It would look like this. And this is still 8. If I integrate that, I get 4 plus 8 plus 3. That's how far I've moved. It adds how far you go in each direction. That's what, 15. Make sense? That's the difference. So when they ask you way over here, explain what that means in the context of this problem, you've got to put it in context. You can't just give it like a cookie cutter definition, right? You've got to put it in context of the situation they're talking about. Okay? So I'm going to write it down here. The integral from 0 to 40 of the absolute value of velocity dt is equal to, why do you keep jumping? The total distance Johanna, whatever, travels from t equals 0 to t equals 40, what, minutes? You okay with that? That's what it means. And then we find it by doing a right Riemann sum, because that's what it says with 4 intervals. So we're going to say the integral from 0 to 40 of the absolute value of v of 2 dt is approximately equal to, and we have 4 rectangles, which means they're all base times height. Okay? Our first rectangle has a base of 12 and a height of 200. Sound good? That's the right side of that. Our next rectangle has a base of 8, because it's a distance of 8 there, and a height of 240. Our next rectangle has a base of 4 and a height of 220. Not negative, we're doing an absolute value here. Okay? And the next one has a base of 16 and a height of 150 on the right-hand side of that. Make sense? So we have 12 by 200. You should write this out. Plus, was 8 by 240. Plus, what was the next one? 4 by 220 and 16 by 150. All right. Now, this without a calculator, so you're going to multiply this out. You should be careful. But since it is the AP test, you don't have to multiply this out. You can leave it like this and just put meters. Yes. Okay. So in the AP test, now again, it has to be straight up like arithmetic. You can't leave like an equation that has to be solved or anything like that. But if it's just multiplication, addition crap, you can leave it like that and that's your answer. You don't have to simplify at all. Well, my test, you're going to simplify. Because multiplication, you have to simplify. That's good practice for that, okay? But in the AP test, if you're worried about making a mistake with arithmetic, let it be. For this, no, this is a non-calculator question. Okay? This is not that bad. You can't multiply this. This is 2,400. Watch me mess up now. Yes. 8 times 240 is... Yeah. It says right Riemann sum. What? Okay. 8 times 200 is 1,600, kids. 8 by 40 is 320. So this is 1920. Good. 4 times 220 is 880 plus 16 times 150. An easier way to think about that, kids, is 8 times 300. Take a 2 away from the 1,600 to make it a nice even number. It's the same thing. 8 times 300 is 2,400. Ready? Look at this. These two make 4,800. How nice is that? With me here? If I take the 80 away from this 800 and put it here, that makes it 2,000. Yeah. Plus another 800. And if you add them together, you get 6,000 plus 2 800s, 7,600 meters. Okay? The only new part there so far was the Riemann sum. C says, notice what they typical of these, after you do a Riemann sum or something, they're going to bring a function in. Yeah, sum or something, yeah. They're going to bring a function in and make you do similar stuff, but now I have to use a calculator or something like that, or by hand. So, Bob is now riding his bicycle, so good. His velocity is modeled by a function, not a table of data, but a function. Find Bob's acceleration. All they want you to do is derive this thing and plug in 5. Make sure you're using the correct units. What's the derivative? A of t is 3t squared, what? Minus 12t. Is that it? Okay, thank you. but we want a of 5. This is such an easy question. That's 75 minus 60. That's 15. And since it's acceleration, meters per minute squared. Since we derived meters per minute, it's meters per minute squared. All these different things. Everybody okay with that? Yeah, that's a surprisingly easy part C to a free response question. All right. And then D, that's all you wanted there, right? Based on the model, find Bob's average velocity from 0 to 10. Average velocity has two formulas, gang. It's the average value of velocity, which looks like this. 1 over 10 minus 0, integral 0 to 10 of velocity. That's the average value of velocity. But it's the same. Oh, crap. Me too. It's also, come on, the window shape popped up and Sarah's too short to get it. Okay? Yo, average velocity is also this, kids. You should know both of these. I'm 100% positive some of y'all are not going to know that when I ask this on a test. Okay? Very good, Marcus. I like your go-getter attitude. Those are the same exact thing. Which one is easiest for us to find right now? Well, I don't know Bob's position, right? Oh, yeah, that's definitely easier. But because they gave me velocity, I'm going to use this. It's 1 over 10, the integral 0 to 10 of, what was it, t cubed? Help me out here. Plus 300 dt. And yeah, they want you to do this by hand. So that's 1 over 10. Remember, this is just power rule. 1/4 t to the 4th minus 2t cubed plus 300t from 0 to 10. We all good on that notation. So let's put a bar at the end. If you put it in brackets, you can just put the numbers on the corners. Yeah. Because I don't know Bob's position. I know his velocity. Right? If they gave me Bob's position, like in a table, and asked for his average velocity, I'd use the position one. Yeah, so you found the average acceleration. Yo, okay, let's write this out here, just to make sure, because this is a super common mistake in which you will not get any points. What's B measured in? What are the units on B? Meters per minute. And what are these numbers down here measured in? Minutes. What are the units on that? That's not a velocity, it's acceleration. That's an average acceleration. Cool? Think about your units. Units are a dead giveaway a lot of times what function you should be using and whether you should be deriving or integrating. Okay? Over here, when we do this integral here, the units on this thing here are meters per minute, right? We're multiplying that by a dt. What are the units on change in time? Minutes, right? Change in time is minutes. So what's meters per minute times minutes? No, we're multiplying by minutes now. It's just meters. But what are the units on this 10 out here? Minutes. So we have meters times 1 over minutes, which is meters per minute, which is a velocity. Make sense? Okay. So that's what, yeah. A lot of times kids know those average value formulas and the average rate change formulas. They know them and they use the wrong function. Think about your units and what you should be putting in there. But now we still got to mechanically work this all out. So we're going to plug in a 10. Do you know that 10 to the 4th power is a 1 with 4 zeros? Yeah, you do. Do you know that 10 to the 3rd power is a 1 with 3 zeros? Well, you should. That's plugging in 10 minus, notice, let's put a bracket here. It's 1/10 times the whole stupid thing. Minus, now we plug in a 0, but luckily when I plug in a 0, they always become zeros. Sound good? Now watch this magic. Since I have a 1/10 out front, I can multiply in 1/10. You don't have to do this. These aren't really difficult to do. But if these are harder numbers, this is a good thing to do. If you multiply in 1 over 10, that 10,000 just becomes a 1,000. That 1,000 just becomes 100. And that 10 becomes a 1. Make sense? Much easier to deal with those smaller numbers. That's 250 minus 200. Let's write it out. Plus 300, and that happens to be 350 meters per minute.